So I'm recording now so that Garrett might get a chance to see this. So we'll see how my artwork does here. So I'm going to recreate what I have on the board here. So here's my XY plane. We were considering y equals x squared, y equals 0, and x equals 2, that bounded region, which would look like this. And we were asking the question, what if we revolved around the y-axis, which with the disc or washer method means we would want to work in terms of y, but my problem right now is in terms of x. Is there a different approach I could take so that I could work in terms of x? And we said, okay, if we're going to do that, then instead of my rectangle running perpendicular to the axis of symmetry, axis of revolution, I should say, it's going to have to run parallel to the axis of revolution. And so if I take this rectangle and again revolve it around the y-axis, the question is, what shape would it make? And we're trying to picture that, and I'm going to try to illustrate it here, and I don't know how good a job I'm going to do. So this point would rotate around. 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 We have something. It ended up looking kind of like that, which is difficult to see. But what it would look like is almost like a roll of toilet paper. You see the roll of toilet paper there? Okay, so I'd have something that's this thick right here, and then this tall that revolves all the way around the y-axis. Are we seeing it? Okay, now let me ask you a question. If I could take that shape, which we're going to call a shell, that's what mathematicians have called that figure. If I could take it and unroll it and lay it flat, what would that look like then?
A washer.
No, it kind of looks like a washer now, but if I could take this figure and cut it right here with a pair of scissors and then unroll it and lay it flat. If I laid it flat, then it would make a big rectangular solid. You're right. It'd look like kind of like that. Okay. Now, what we want to do is think about what the volume of that rectangular solid would be then. Well, to get that, I'd have to take the length times the width times, if we called this the height. Okay. Now, let's think about the height first of all. Do you see that the height here would be the same as the height right here of my original rectangle? Here's my original representative rectangle. So the height of the rectangle would be represented by that this point on my rectangular solid. Okay? So we'll call that H. Now, what about the width down here? The width of my rectangular solid would be the width of my original rectangle right there. We okay with that? Okay. Now, if that's going to be my rectangle right there, and that's so I partitioned this into a whole bunch of rectangles, I'm going to call that my delta x. Okay, it's the width of one of my rectangles. So This height is the blue height on the rectangle. This width is the delta x. Now, what about this length here? You see where it's going to come from? That's right, the circumference right here. The circumference. Well, what's the formula for circumference?
It's the same thing. Pi r squared.
That's the formula for area. You were close though. It's 2 pi r. It's 2 pi times radius. Do you see that the radius of this circle in here would be this distance right here? Okay. Now, your book refers to that distance, which, if you think about it, it's the distance from the rectangle to the axis of revolution. That's what it is. Your book calls that P. That distance. So that's the radius. So this length would actually be 2 times pi times P. Okay, now let's take the length times the width times the height and get the volume of this thing, which is the volume of this thing. Okay, so 2 pi p h delta x, and what that represents is the volume of one shell. Am I making sense, Austin? Am I making sense, Aaron? Okay, that's the volume of one shell. Now, how do I get the volume of the whole region then? Well, I do a whole bunch of rectangles in here, right? I put an infinite number of rectangles, revolve all of them, get a whole bunch of shells, get an infinite number of shells, and how do I add up an infinite number of shells? With an integral. That's right. So if we now integrate, put an integral in here, 2 pi is going to be a constant. If I put an integral in there, now I've got a way to add up the volume of all those shells, which gives me the volume of the solid of revolution. And now I've got a way that if I have a vertical axis of symmetry, I can work in terms of x. And conversely, if I have an horizontal axis of symmetry, I can work axis of symmetry, axis of revolution, then I can work in terms of y. Okay, now let's. So if we formalize this notion, we can write up the shell method as follows. Okay, let me just get that off. Okay, shell method, and this is used again to find the volumes of solids of revolution. And here's what it says. It says if you have a horizontal axis of revolution, and here's the major difference between it and the disk and washer method, then we're going to work in terms of y. So the volume would equal the 2 pi that we found earlier times the integral from c to d of p of y, h of y, dy. And we'll talk about what the p of y is in just a moment. And the h of y is going to be the height of your rectangle. If we have a vertical axis of revolution, then we're going to work in terms of x. So the volume will equal 2 pi times the integral from a to b of p of x, h of x, dx. Now this next little tidbit is what helps me make the most sense out of the shell method. So this is really important. P of x and P of y. What are those? To find those, what you want to do is find the distance from the rectangle, and when I say the rectangle, I mean the representative rectangle, to the axis of revolution. So if you get that part down, that makes the shell method a lot easier, if you understand that. And one other note I want to remind you of is this, and it's important. With the shell method, the representative rectangle is parallel to the axis of revolution. And that's what allows us to work in the other variable.
Is this for both vertical and horizontal, or just for?
Yeah, whatever your axis of revolution is, if it's vertical, then you're going to draw your representative rectangle vertical. If it's horizontal, you're going to draw your representative rectangle horizontal. It's always going to be parallel. Well, let's see if we can work a couple problems using the shell method. Okay. Example 1 is found on page 459. Here's what it says. It's actually on page 458. Find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x cubed and the x-axis and then they put us on an interval. They tell us that 0 is less than or equal to x is less than or equal to 1. And we're supposed to take that about the y-axis. Well, let's see if we can come up with a graph. We don't have to have a real big graph because we're only looking at x values from 0 to 1. So, and we're bounded by the x-axis. So we don't have a whole lot going on here. So let's say here's an x value of 1. And I'm just going to use a t-table to help me generate the graph then. So if I put 0 in for x, then y would equal 0 minus 0 cubed, which is also 0. So 0, 0 is on this graph. And if I put 1 in for x, I would have 1 minus 1 cubed, which is also 0. So I guess we better figure out what it's doing in between. Maybe I'll put a half in for x. A half minus a half cubed would be a half minus an eighth, which would be 3/8. So 1/2 on 3/8 units up, which would be somewhere in that neighborhood. So it looks like the graph's doing just something like that on the interval from 0 to 1. and we're going to revolve that around the y-axis. Okay, now that's a vertical axis of symmetry. So before today we only had the disk or the washer method, and if I was going to use those on this problem, which I guess it'd have to be the washer method because we'd have a hole. If I was going to use those, then I'd have to work in terms of y, which means I'd have to solve this equation for x. And that looks like quite a chore. That's a lot of work. So let's use the shell method, which allows us to work in terms of x when we have a vertical axis of revolution. Okay, so we know that with the shell method that our representative rectangle runs parallel to the axis of symmetry. So it's going to look like that. And we know we're going to work in terms of x because we have a vertical axis of revolution. So the formula went like this: 2 pi times the integral from a to b of p of x, h of x, dx. Okay, which for us is going to be 2 pi. I'm in terms of x, so my lower bounds need to be thought of in terms of left to right. So my leftmost endpoint is here, my rightmost endpoint is there, and those have x values of 0 and 1. And now I need my p of x. Now what is p of x? We always have to remember what it says up here. P of x, by definition, or what I'm telling you, is the distance from the rectangle to the axis of revolution. Okay? So, for us, on this problem, it would be this distance right here, denoted in red. So this is a little bit tricky for some students, but I just want you to think about this. If we thought about this point right here on the graph, which would have the same x-coordinate as this distance I've denoted at the bottom, that would be the point x, and then the y value would be the function evaluated at x, f of x, right? Okay, so then what if this point is x f of x, then what's this distance right here? Just be x, wouldn't it? Because that's how I got to this point. I went that many units to the right, and then f of x units up. So listen, if you're measuring from your rectangle back to the y-axis, that distance is x. Did you hear that? The distance from your rectangle back to the y-axis is x. We're going to use that on many, many problems. So this p of x on this problem is x. The h of x is the height of your rectangle. Okay, well, that's going to be this distance here, which is defined by the function in this case, which is, I don't remember what it is. What was it? X minus x cubed? All right. So there's the integral that we need to find the volume. That's not too bad. And very nice because, again, we got to work in terms of x. All right, well, let's go ahead and finish this first one off. I know that's not a real difficult integral to work and evaluate, but just to take the process from beginning to end. So I'd have 2 pi times the integral from 0 to 1 of x squared minus x to the 4th dx. which would give me 2 pi times x cubed over 3 minus x to the 5th over 5, evaluated from 0 to 1. It's kind of an ugly 0. Alright, throwing the 1 in there, that'll give me 2 pi times 1 cubed over 3, or a third, minus 1 to the 5th over 5, or a fifth. And if you put the 0 into both of those, you're going to get 0. Third minus a fifth, what's that? Let's see, times 5 times 5 would be 5 over 15 times 3 times 3. Be 5 over 15 minus 3 over 15, which would be 2 over 15. And 2 pi times 2 over 15 would be 4/15 pi for the volume. So let's work a couple more of these just to make sure that we got the notion. So example 2 is on page 459, and it says the following. Find the volume of the solid of revolution formed by revolving the region bounded by the graph of x is equal to e to the negative y squared and the y-axis about the x-axis. So you can see here that we're probably going to want to use the shell method because we have a problem that's in terms of y, but we're going to be revolving around a horizontal axis of revolution, the x-axis. So we're going to have to figure something out about our graph here. So we'll have to chew on that a bit. So I guess what we'll do is we'll put values in for y into a t-table and maybe solve for x to help us get a graph. So maybe we could put 0 in for y. It might be a good one because then 0 squared would be 0. E to the negative 0 would be e to the 0. E to the 0 is equal to 1. So we know that 1, 0 is on this graph. Putting 1 in for y might be fairly simple. Let's see how that works out. If I put 1 in for y, I'd have 1 squared is 1, so it'd give me e to the negative 1. So x would equal e to the negative 1, which would be the same thing as 1 over e. Well, let's think about that. You might remember that e is approximately equal to 2.718 blah 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 blah. So let's put approximately equal 1 over 2.7 . 1 over 3 would be a third. So this would be a little bit more than that. So a little bit more than a third. So approximately a third and 1. So we're going to have a point like somewhere in this neighborhood. I was thinking for a moment about getting other points here, but the problem tells us, if you look in your textbook, I didn't realize this a moment ago, that they put us on the interval 0 less than or equal to y less than or equal to 1. So the graph's just going to go from here to there because that is the interval from 0 to 1. So our bounded region looks like this. It's all this stuff in here. And we're going to revolve that around the x-axis. Which means our rectangle needs to run parallel to the x-axis. So it needs to run like this. So far so good? Okay, I think we're ready to set up our integral now. So, since we're going about a horizontal axis of symmetry and we're in terms of y, we know we want to use the shell method. So we'll take 2 pi times the integral from our lowest point to our highest point because we're in terms of y. Our lowest point in our bounded region has a y value of 0 and our highest point in our bounded region has a y value of 1. So you're going to integrate from 0 to 1. Okay, and then we need our p of y. P of y is the distance from the rectangle to the axis of revolution. Now, on our last problem, we were in terms of x, and we were measuring the distance back to the y-axis, right? And we said that that's equal to x. So if you're in terms of y and you're measuring the distance back to the x-axis, what's that distance going to be?
Y.
It's just going to be y. That's right. Distance there is just y. And then your h of y is the height of the rectangle. That's that distance there. That's defined by the curve in this case, which is e to the negative y squared dy. Everybody golden there? All right, well, this will give us a chance to remember how to integrate with some e's involved. So obviously there's no rule that fits this integral, so we're going to have to do a u substitution. So I could let u be equal to negative y squared. Du would equal negative 2y dy. So negative a half du is going to equal y dy. Okay, I'll bring this over here now. So I have 2 pi. It's the integral from 0 to 1. And evidently I need to have a factor of negative a half along with that and a du. So negative a half out here, du, and that's going to wipe out y and dy and leave me with e to the u. And here the 2's will cancel, so I'll just have negative pi out there. And if you integrate e to the u, you get e to the u. And by the way, I made a mistake and you guys didn't stop me. Do you know what mistake I made? 0 and 1 are my lower and upper bounds in terms of y. And right now I'm in terms of u. So I really should not have included those here. So negative pi times e to the u is really negative pi times e to the negative y squared And now I'm back in terms of y, so now I can include my lower and upper bounds of 0 and 1. Which will give me negative pi times e to the negative 1 squared, or 1, minus e to the negative 0 squared, which would just be e to the 0, or 1. And if I multiply through with the negative pi, I'll have negative pi e to the negative 1, which is really negative pi over e to the positive 1 plus pi. So there's your volume. Let's do a problem that we did yesterday. Let's do it in a different way. Example 3. We have a bounded region with y equals x squared plus 1, y equals 0, x equals 0, and x equals 1. We're supposed to revolve that around the y-axis. Okay. And yesterday we said the graph looks like this. It'd be a parabola that's been moved up 1. Y equals 0 is the x-axis, x equals 0 is the y-axis, and x equals 1 obviously is going to be a vertical line. And we have this bounded region. Now rotate that around the y-axis. So here's what we had to do yesterday. We had to draw our representative rectangle perpendicular to the axis of revolution, and that created a lot of problems because number one, we had to work in terms of y then if we're going around a vertical axis of revolution. That was the first problem. And the second problem was when I drew my rectangles, this rectangle on the bottom down here, if you look at it and rotate it, there's not going to be a hole. So on that part, we'd use the disk method. But up here, there is a hole. So on that part, we had to use the washer method. And it got kind of messy. So let's look at how we can work this problem using the shell method. That's going to allow us to work in terms of x, and it's going to make the problem a lot cleaner for us. So instead of rectangles perpendicular, now we can draw our rectangle parallel. The red rectangle is the one we need, and we can work in terms of x. So we'll go 2 pi times the integral. If we're going to be in terms of x, we'll go from the left endpoint to the right endpoint of our bounded region. So from here to there, we'd have x coordinates of 0 and 1. There's my p of x. What's my p of x going to be, fellas? X. That's right. And then here's my h of x. It's the height of the rectangle, which is defined by the curve, x squared plus 1. And we slap a dx on that, and we evaluate that integral, and we'll have it. So that problem is a lot cleaner by using the shell method than it was by using both the disk and the washer method. And I'll let you finish this integral. They show how it evaluates on page 460, and we get 3 pi over 2, just like we did yesterday. Austin, you had comment?